Welcome to the Throttle Up podcast, a behind-the-scenes look at what it takes to build and launch a new class of rocket propulsion. Hosted by Sasha Derry, founder and CEO of bluShift Aerospace, and storyteller and entrepreneur Justin Starbird. This podcast follows the real work behind the mission. From early design and propulsion development to testing, capital, partnerships, and the path to launch, each episode brings you inside the process as it unfolds. This is your front row seat to watching bluShift Aerospace take off.
Welcome back to the Throttle Up podcast presented by bluShift Aerospace. My name is Justin Starbird, and I'm excited I get to welcome back Luke Saindon, the lead mechanical engineer, and Gerard Desjardins, the lead propulsion test engineer for bluShift Aerospace. Guys, I guess the first one wasn't bad. You came back for another episode.
Yeah, this is fun to get into the weeds about it all.
I think we could probably talk for weeks about rockets. It's not that hard.
Yeah.
Well, the good thing is this podcast is dedicated to rockets, so we're in the right spot today. So that's great. The last time that we spoke, we talked a lot about the engineering that goes into bluShift and what it's actually taken to get to this point. We're preparing for a test in a couple of weeks, so we'll actually have a preview about that closer to the actual test. But we've gotten a lot of questions from folks in our community talking about what it takes to actually fly. So, we spoke a little bit about the sexy, looking at a rocket launch and seeing it across the horizon and into the atmosphere. But that's, where people often focus. How much of getting to flight is actually about the infrastructure, safety? I know, Gerard, you've talked a lot about that in the previous episode. Logistics, procedures, what you talked about, Luke, or the operations. How much of all of those things do you spend time on prior to seeing a rocket lift off?
I mean, I'll start by saying I've spent the last 2 years pretty much working on our appropriate FAA licensing. So, that's not just a matter of lots of pointless paperwork and red tape. It's to get the answers they need for your flight is a big chunk of the work that's required to design your whole flight profile. So simulating the flight and making sure that it goes within your safety zone and coming up with all the statistics around the flight and all the possible places it could go. And those are the sort of things that you need to answer for them, that you'd have to answer for any safe flight, regardless of if the FAA was overseeing it or not. And so that's been my life for quite some time now. So that's one big major element that is not just, loading the tanks with propellant and pressing go. So
how about for you, Gerard?
Yeah, one thing that's been blowing my mind over the past few months as we prepare to submit our Part 450 FAA launch license is how much statistics and simulation goes into this. I worked in the commercial aviation industry for about 5 years. And at that time, which, also FAA regulated, I was blown away by how much analysis and focus they put on making sure, your jet engine is safe and you'll have a good flight. And the same goes for the commercial space industry. You got to know exactly what's on your vehicle. You got to know what could happen, and you got to determine what's the probability that it's going to happen for a vehicle that has, hundreds of thousands, if not millions of components. And so you can imagine how much compute power and time goes into figuring that out. It's kind of, like I said, it's mind blowing.
Yeah, you have to simulate a cloud of trajectories And then for every point in that time, you've got to say, what if this happened? What if that happened? What if, A through Z scenarios happened? And then for each of those scenarios, you'd be like, okay, where did this bolt go? Where did this nut go? Where did this valve go? Where did this fin go? And each one of those has a trajectory. And then, so it's a tall order that's necessary. But just in terms of preparation before a flight, before you put any hardware on the ground, that's one of the biggest efforts.
Yeah. I get, people don't see that, right? I mean, you either see you only see what goes up in the air, or what doesn't, sometimes spectacularly what doesn't, right? So to that end, you've got to, I guess I never really thought about there could be millions of components on there, and the nut, the bolt, the valve, the sensor that is careening off of something if it goes in the wrong direction. That is wild.
Yeah. It's millions and millions of simulations, by each simulation, I mean like a modeled trajectory of where something will land. And then you've got to do that for every weather condition that you plan to fly in. And then how accurately do you know the weather? How accurately are you measuring it? What's the uncertainty of the wind gusts? What's the uncertainty of how much propellant you actually loaded? Like, you think you have loaded 1,800 kilograms of oxidizer, but where would it go if you actually loaded 1,805 kilograms, because your load cell uncertainty is plus or minus 1.5 kilograms,
Yeah. Wow. All right. So I guess that leads me to my next question. What's the difference between a successful engine test and a successful flight?
I think the stakes always feel pretty high when you've got that much power on a test stand versus in flight. But during a launch, the stakes are at the peak. This is the ultimate test where you are everything that you've predicted that will happen. It will happen, or something will go wrong, and you don't really know when you push the button. Statistics, even with millions of iterations and calculations, statistics kind of don't take care of everything, right? There's always things that you can't account for. So I guess kind of the stakes being higher, and kind of delivering. It feels a lot more like delivering a final product to your customer. Like, this is what I made. This is what I did. It's yours now, or we brought you up there, or we don't. That's the aspect of flight. That's it can be very nerve-wracking, but both for tests and flight, the way that I deal with that is just thousands of hours of preparation and procedure, testing those procedures, simulating faults, and just being prepared. That's the only thing you can do, really.
Yeah.
The stakes are higher because the consequences of a failure are higher, but the stakes are also, and the nerves are higher because you just stack that many more things that could go wrong on top of each other, right? So with a test, maybe you have 6 things, just as a wild, throw that number out there, that each, have 95% chance of working. So it's 95% chance that thing A works times 95% chance thing B works times 95%. And, it's 95 times 95 6 times. And you're like, okay, it works out to like 75% chance the whole chain works, right? You're 75%. Okay, you double that because now you have, your launch tower, and you've got all your avionics, and you've got the airframe, and you've got loading all the propellants and the recovery systems. So now you've got, 12 or 13 things that all have 95% chance, and now you're down to 50% chance, So the math is against you.
Luke and I have done a few high-powered rocket launches together, and another comparison to make is a lot of people memorize sports stats. I don't have a mind for that, but um, seared into your memory is what happened on launch day and what went wrong, what went right, the struggles that, you went through and overcame.
Yeah.
That's the kind of like stats that we remember and really focus on.
So I got to ask then, are you by nature more optimistic or pessimistic because you have to run these models and the math says that there's a 50-50 chance that it's not going to work. Is that a 50-50 chance that it's not going to work or a 50-50 chance that it will work for you?
I think by the time you're done running millions of simulations, you're like, well, if it doesn't work, there's nothing else I could have done. Like and let's go. Like it's time to launch. Like it's time to test, time to launch. Done waiting, done, wrestling with our computers. We just gotta do it. So I think in the end, I end up feeling a lot more optimistic and confident. Yeah.
How about for you, Luke?
I think you have to be a little bit of an optimist to play this game, but I think for me, it's very much of like plan for the worst and hope for the best kind of thing, really manage your expectations.
Yeah.
And the only way I feel comfortable is if you can be totally honest with yourself that you have prepared for every bad outcome that you can possibly think of. That's how I can go to sleep at night, is like knowing like we have turned over every single rock that we can think of, and made sure that if that happens, we have a controlled situation. So as long as you've prepared to the best of your ability, then it's fun to hope for the best, but as long as you're not necessarily expecting it and you've prepared for the worst.
So
yeah, it'd be far more devastating to get up to that point and then just not push the button, not do it. Like that would be far worse.
So I'm going to go out of order here because I have a lot of questions about this because of course I've not been part of this or privy to it other than watching on TV or following along in the press as you guys have done this in the past. But when you think about all those elements that go right or they could go wrong, what are some things that you've actually unplanned milestone that that the team still learned from, but you were like, oh wow, that could have been a lot worse? Have you had any of those moments?
Oh yeah.
Of course.
That you can talk about, right? I don't want to get
no. Thankfully, nothing. Really, we haven't. Everything has been more or less controlled, but we've definitely had some moments of learning. Can think of a couple. Nozzle design, for example. It seems like every rocket company's got an O-ring story. So we've definitely had some learning around, like, if you're like, it'll probably be okay, let's give it a shot. And, this O-ring groove is, it's a little out of tolerance, but we think it'll be fine. And you put it on and you just melt the end off the entire motor. So
when an engineer says we think it'll be fine, it's more of like we have a percentage in mind. We've done the calculations. It's not just Kentucky windage, but still, for us, it feels a lot like we don't know. We just have to go for it, even though there is actually a lot of calculation behind it.
In this case, it was sort of like, well, it's the nozzle we have. We want to run this test. If it goes wrong, it's not going to be the end of the world kind of situation. So you over time develop an intuition of like what things you can sort of let slide as, never in terms of a safety concern, but in terms of like, will the test just totally fail? You sort of develop an intuition of like, yeah, that's probably even if it goes wrong, it's not going to totally ruin the day. And so you develop a pretty good sense of intuition over time. You're always adding to that, but the only way you can kind of develop that feel is with a lot of tests that have gone sideways.
I feel like it's going to be a badge of honor then if one of the tests goes sideways. You're like, well, now you're part of the club.
Yeah, I mean, you can't avoid it. You just try to do as little damage to your infrastructure and expensive hardware as possible in the process.
Gerard, you mentioned getting all the way to the end and then needing to scrub a test or a launch. How often has that happened, or what led to calling off a test?
Yeah, I mean, I was kind of talking about, it's better to fail than have never tried, but there's also been some instances where we got to scrub tests. And
what's the farthest we've gotten along in a 24-inch test and then scrubbed? I was actually just trying to think. Have we ever loaded propellant?
Fully loaded.
Have we fully loaded and then scrubbed? Has that actually happened with the 24-inch motor?
Not in the case where we were using not for the 60-second burns.
Yeah.
But before we got to the point where we're doing 60-second burns, we were doing 10, 15, 20-second burns with a lot less propellant. And there was definitely times where we loaded the propellant, everything's ready to go. We're streaming live on YouTube. Yeah. And a lot of pressure, and then we just have to call it off.
Well, that's what happened to our very first test. Is we test all of our fire extinguishers before a test, and one of the valves that controls the fire extinguisher system stuck on. So we tested the fire extinguisher, and it just kept running, and we couldn't turn it off, and we just drained our entire fire suppression system, and then couldn't test because we couldn't turn off our fire extinguisher.
Oh man, that's wild.
Yeah. But you're also, as we talk about everything that goes on that you don't see, the people who are watching on YouTube, what they don't see is that we've done so many subsystem tests leading to that point that we can figure out what went wrong pretty quickly, or, you can narrow it down. And so, you don't really see all the bottom bricks of the pyramid that you're building up, and really a completed test is just the top brick, which is at that point it's just kind of just another brick, but
you get the compounded effect of you've done all these subsystem tests that are all 99% sure that they're going to work. So when you do a full test, you have to multiply all those together and you end up with 75% chance it'll work. Hopefully better. The only way you improve that is make everything 99.99% sure. I think our igniters have been one of the biggest challenges that has caused several tests to be stopped, which we test before we load the propellant. So usually we don't waste a bunch of oxidizer, but it still has ruined several test days as our igniters not working properly. So that's been one of the bigger challenges for subsystem testing that we've put a lot of work into, and still need to work on a little bit. So in terms of frustrations and failures, igniters have been a pain in the butt.
Yeah. Well, starters in cars, right? I mean, anything that gets you going, like it's so annoying when everything else is working, right? So thinking about the data though that you're getting out of that, and I like the analogy, Gerard, of a pyramid, or the last brick on something where it just all fits together, and that's a spectacular, test or launch that everybody sees, not realizing how many steps went into getting to that point. Thinking about the steps that go into that and the test that you're attempting to solve for, have you ever had a test that comes back afterwards and you're reviewing data and discovered something completely different than what you maybe expected at the onset? Good or bad?
Yeah, I mean, this is being a startup, like having a very unique propulsion system. This is not just another liquid oxygen kerosene rocket engine. This is like, bio-derived, grown on the farm and
as
put
a
it and
hybrid,
get
which
into
haven't been
space.
done much.
Yeah. And so there's so much that we learn. Um,
I think
every single test, it feels like.
Yeah. I think a lot of times we fail to fix the thing we were trying to fix. So if that's kind of like, that's what happens most of the time when there's a, unexpected thing, so to speak, is we make a change that we're hoping will solve a problem and it just does bupkis, it doesn't help at all. So that's a pretty common failure, if you want to call it that. Process of elimination, maybe.
Yeah. What kind of, so thinking about not fixing the thing that you were hoping to fix, are there risks or failure points that people outside of the industry or, watching bluShift rarely think about, but are so critical to the successful, flight program?
Yeah, definitely. I mean, I think people, just like any industry, we don't really see what's going on behind the late hours of the night or behind closed doors. I think really, like anything else, is a lot of time, a lot of failure occurs, and overcoming that failure. So I think kind of like any other profession, it's just learning every day and then pushing forward.
I think one kind of boring failure that is one of the worst kind to have is when your data acquisition system fails to function. Because then you run a test and maybe it's a great test, but if you have no measurements because something went wrong with your data acquisition, that's almost the worst feeling. Because then you can't, it's hard to learn anything from it. You just sort of had a spectacle.
Even then it's you can come up with ingenious ways to get measurements that maybe you wanted a thrust measurement, but your load cell wasn't working. Well, what was the pressure inside the chamber, and can we back out what the thrust was from that, for example? You come up with kind of ingenious ways to get around those hurdles.
Yeah. Well, that's why they call you rocket scientists, right? Like that's why you gotta come up with, you're nothing if not persistent and resilient to overcome all these different elements that are stacked against you.
Mm-hmm.
Yeah, it's you never, in those sort of situations, you never quite get the fidelity that you want from the data, but that can be fun in its own way, as trying to be, detectives about it. Like we've had, once when our system failed, we had a screen recording of like our dashboard that's just it updates once or twice a second, and it's just like a crappy screen capture basically. And we went through it frame by frame and just wrote down the values on each one of the gauges and, got our rough traces. So it's a bummer when that sort of thing happens though.
Well, so thinking of that, what's maybe, Luke, this is probably more to some of the stuff you've spoken about today and in the previous episode, but, lessons that you've learned that could never have been learned through the modeling or the simulation or even theory alone that had to be tested that came out that you're like, oh, look at that.
I mean, so many things. It's, I keep coming back to sort of the big three things that are really hard to simulate are like combustion stability. So the transients and like the oscillations and vibrations, those are really hard to predict. The combustion efficiency, so how well do all the gases mix? And and combust before they leave the nozzle. And then another one would be something we call regression rate, which is how quickly does the solid fuel in our hybrid motor erode from the fuel grain into the combustion chamber. And we've, I never quite know what that's going to look like before a test. So that's the first thing I always do is analyze the data to see what those three metrics look like, because those are always the biggest question marks that I know what I'm hoping for, but we don't really know what they're going to be until we've run the test.
Anything for you, Gerard, that you've thought, in testing that, there was no way that you could have accounted for in simulation?
Well, it's kind of making me think of, being a test engineer, preparing your apparatus for the go time, and being the one to operate it is something that you can't simulate very well. I mean, you could practice, but when it comes down to the moment that you are, and I'm talking about being physically on site, operating these high pressure systems, and being the one to open valves, and being the last hands to touch things, being the set of eyes on the ground to confirm that things are okay. It's very difficult to simulate that. You just got to do it over and over again. And then also being the one to be directing, like, okay, we've confirmed that all these subsystems are a go, then we're going to press the button. It's not something you can really simulate.
Yeah, you're making me think of, Gerard, also like how when a test is running, there's some automated shutdowns that will, some things are automated in terms of if this, then do that. But there's also some things that are kind of subjective where we have procedures and scenarios written down where, like, if you see, fire on this part of the stand, then scrub the test or do this. And sort of like, well, what if we play through all these different scenarios? Like, well, what if this happens? Then what are we going to do? And a lot of them you can't really automate, and you don't actually even know exactly how likely it is to actually happen. But then once you run when you're running the test, these things that felt pretty objective get a lot more subjective, and it's really interesting to sort of, it's hard to predict exactly how the human in the loop is going to process the information coming in and make these calls in real time. And that's why automation is important, because humans aren't particularly good at that. But sort of it's pretty hard to simulate how the control room will react to different situations ahead of time.
All right. So take us inside your minds as you're running through, maybe Gerard, the prep for the test, and Luke, like, as the test is going on, what are those things going through your minds?
At this point, we've done so many tests that we have a really good methodology going, really good procedures. So at this point, doesn't really hit you until the point where you leave the test site, and you are locked and loaded. There's nothing
out of the exclusion zone.
Yeah, we operate our tests remotely. So leaving the test site is like, all right, I can't do anything physically here. It's all remote from then on, and so I guess that feeling is it's pretty powerful.
That's awesome. How about for you, Luke? As it's going on, what are you thinking through? What are you mentioned if this, then that. Is that truly viable?
I mean, the biggest the biggest push and pull in my mind is always, say we're running a test and it's really unstable. The combustion is like popping and you're getting pressure spikes and things that can be dangerous to the motor. I mean, it's within a bunker, so it's not really, it's going to take itself out in some of our infrastructure, and it's going to be a bad day from just expense and timeline wise. So I want to stop it because it has a chance of being really expensive, but I really want the data. So let it run.
Who makes that call? Is it your calls or is it Sasha? Who makes those calls?
It's Gerard at the end of the day as the operator.
Whoever's operating whoever's the test operator.
And then,
but it's Sasha's really hard to.
Hey, let me see your checkbook.
Checkbook's been thrown out the window at that point.
But yeah, because everyone has a different tolerance of where that line is. That sort of tug of war of sort of when to cry uncle is a real interesting one. So that's usually what's going through my head is usually there's something that I'm a little obviously we're still testing, right? We're still learning stuff. So there's always something that's like, well, that's not quite what I was hoping, and you sort of, how far do you let that go before you're like, okay, this is going to get expensive. Stop.
Yeah.
Versus, well, this is interesting. I want this data. Keep going.
That's cool. All right, guys. I mean, we're getting closer to the next big test day, and we're alluding to it in a couple weeks. We'll do a preview of that. All right. So to get you guys out of here, what are you hoping to, accomplish in the next 4 to 6 weeks leading up to the test that you can share?
We've got some manufacturing to do, some sourcing parts and getting parts in. We're increasing the size of our engine. So we've just got some updates to make, and just kind of wrapping up, design and analysis and getting into the manufacturing and testing.
Yeah, we have a few really exciting updates on this test that I think have been thought through really carefully, and I'm really excited to see what they do. We're going for some big updates on stability improvements and some smaller updates for combustion efficiency improvements. But I have a part that I designed for trying to improve the stability that I'm really excited to see if it works or not. It's one of those things where there's some theory to back it up. And it's been pretty carefully formulated, but it's still very much, it's just a theory. It's a hypothesis. But I think it's the best, most careful effort we've put towards that problem so far. And I'm just really looking forward to seeing what happens with that. It'll be a cool piece of technology in the motor if it works. There's a couple of known solutions to this issue that, in our opinion, aren't quite as elegant of a solution. So if this works, it'll be pretty neat, and I'll personally be really excited about it. So that's kind of the biggest thing on the line for me as an engineer for this test, is seeing if that solution shakes out or not.
Yeah. Well, it sounds like we're preparing for a, recap episode to talk about, what was so spectacular about its, elegance, or why did it fail?
Yeah,
right. In either case, we'll be breaking it down. So, well,
either way, it's going to be a lot of fun.
Yeah, no kidding. I'm looking forward to it. There's no doubt about that. So I really appreciate you guys jumping on for a second episode to talk about, what goes on and what it actually takes to make one of these rockets fly. This has been great.
Yeah. thanks again for having us.
Yeah, thanks for having us.
No problem. On behalf of my guest today, Luke Saindon, the lead mechanical engineer, and Gerard Desjardins, lead propulsion test engineer for bluShift Aerospace. You've been hopefully watching or listening to the Throttle Up podcast. Until next time.